Hello friends, I am Vijay Kumar S. Biradar, working as assistant professor in electrical engineering department and HOD general science and engineering at NB Navle Singhad College of Engineering, Solapur, with 19 years of experience. We are going to discuss the subject Control System 2 for T electrical engineering, and the topic is observer based approach for the control system design in state space. Previously, we discussed about the full order and reduced order observer design. In that, we need to design or we need to determine the observer gain matrix. So the three methods which are used to determine the observer gain matrix are transformation matrix Q, direct substitution method, and Ackermann's formula. We already seen these three methods for the pole placement or controller design. Now the same methods are there for the observer design also. So for observer design using the transformation matrix is that Ke is equal to Q into the equation alpha n minus an. Second row becomes alpha n minus 1 minus an minus 1, and the last row becomes alpha 1 minus a1, where this Q is obtained as the W into n transpose its inverse into the matrix same as, where Q is W into n transpose its inverse, where n is C transpose, A transpose, C transpose up to the A transpose n minus 1 C transpose, and W is obtained from an minus 1 an minus 2 and up to an a1, and the last element is 1. Then shifting this towards the left hand side for every row with one element, we'll obtain the last row becomes 1 and remaining elements in the row will be 0. With this we are going to get the value of Ke. So the same can be obtained from the controller or the state feedback gain matrix K. This Ke is nothing but, we seen the dual property, so this Ke is equal to K transpose. So we'll obtain the value of Ke as alpha n minus an, alpha n minus 1 minus an minus 1, and alpha 1 minus a1. By direct substitution method also we can obtain K is equal to K1, K2, K3 and Kn. In this direct substitution method we need to compare the coefficients, and we can obtain the values of this K1, K2 up to Kn. Then using Ackermann's formula, the value of state feedback gain matrix K can be obtained with this equation, and for dual of this system it is Z dot is equal to A transpose Z plus C transpose V, n is equal to B transpose Z. This is the duality we use. Then the K becomes 0 0 all and the last element is 1. Then the matrix B becomes, here it is C transpose A transpose C transpose A transpose square C transpose and up to A transpose raised to n minus 1 C transpose its inverse into phi of A transpose. Therefore we will obtain the value of Ke as the transpose of this whole equation, that is K transpose. Then Ke is simplified and it is written as K is equal to phi of A, then C CA raised to n minus 2 CA raised to n minus 1 its inverse into a column matrix 0 0 0 with the last element as 1. So with this direct equation one can get the value of Ke, that is the observer gain matrix. Few points related to the observer gain matrix. The feedback signal through the observer gain matrix Ke serves as the correction signal to the plant model to account for the unknowns in the plant, as it is an observer. If significant unknowns are involved, the feedback signal through the matrix Ke should be relatively large. However, if the output signal is contaminated significantly by disturbances and measurement noise, then the output Y is not reliable and the feedback signal through the matrix Ke should be relatively small. The observer gain matrix Ke depends on the desired characteristic equation, that is S minus beta 1 into S minus beta 2 up to S minus beta n is equal to 0. The observer poles must be 2 to 5 times faster than the controller poles to make sure the observation error converges to 0 very quickly. So this is the selection between the controller and observer values. This means that observer estimation error decays 2 to 5 times faster than does the state vector x. Such faster decays of the observer error compared with the desired dynamics makes the controller poles dominant the system response. It is important to note that if sensor noise is considerable, we may choose the observer poles to be slower than 2 times of the controller poles, so that the bandwidth of the system will become lower and the smooth the noise. In this case, the system response will be strongly influenced by the observer poles. If the observer poles are located to the right of the controller poles in the left half of S plane, the system response will be dominated by the observer poles rather than the control poles. In the design of the state observer, it is determined or it is desirable to determine the several observer gain matrices Ke based on several different desired characteristic equations. For each of the several different matrices Ke, simulation test must be run to evaluate the resulting system performance. Then we select the best Ke for viewpoint of overall system performance. In many practical cases, the selection of the best matrix Ke boils down to a compromise between speedy response and the sensitivity to disturbance and noise. So these are few things which we discussed as a theory part of this observer design. So for better understanding, we'll have an example. So consider the system which is given by the state model. We use the observer based approach to design state feedback control such as u is equal to minus k x cap. Design a full order state observer. Assume that the desired eigenvalues of the observer matrix are beta is equal to minus 10 and beta 2 is equal to minus 10. Therefore, two poles we need to place at minus 10, minus 10. So we'll examine the observability first, as it is the necessary and sufficient condition. So rank of observability matrix is 2. Therefore, the system is completely state observable and the determination of desired observable gain matrix is possible. So as the given system is in observable canonical form, therefore the value of Q is equal to I. If this system is not in observable canonical form, then we can use this Q is equal to that W into N transpose its inverse. We can get that and we can substitute that as a value of Q. Therefore, the characteristic equation of the given system is S square minus 20.6 is equal to 0. Therefore, A1 is equal to 0 and A2 is equal to minus 20.6. We'll got the values of A1 and A2. Then the desired characteristic equation of the system is written as S square plus 20S plus 100. Therefore, alpha 1 is equal to 20, alpha 2 is equal to 100. And we can obtain the value of Ke, which is alpha 2 minus A2 and alpha 1 minus A1. Therefore, it is obtained as 120.6 and 20. This is the observer gain matrix by the first, that is the transformation method. Then for second method, it is directly calculated from the characteristic equation of the observer error matrix, which is determinant of Si minus A plus Ke into C is equal to 0. Therefore, Ke is Ke1 and Ke2. So we'll substitute, we'll compare the coefficients of S square, S and constant, and we'll get Ke is equal to 120.6 and 20. So this is using the direct substitution method. Then for Ackermann's formula, we'll calculate the phi of A square, then phi of A becomes this one, then C A its inverse can be calculated and substituted. So we'll get K is equal to again the same value using the Ackermann's formula also. So regardless of the method employed, we'll get the same values for the controller